Hey everyone, and welcome. Today we're diving into a Leetcode problem called largest color value in a directed graph. It sounds a bit complex with graphs and colors, but don't worry, we'll break it down step by step. Our goal is to understand the problem, and then figure out an efficient way to solve it. Ready? Let's go. So what's the challenge here? We're given a directed graph, which means edges have a direction, like one-way streets. Each node in this graph has a color, represented by a lowercase English letter. We're also given a list of these edges. Our main task is to find any path in this graph, and for that path, we need to figure out which color appears most often. The count of that most frequent color is what the problem calls the color value of the path. We want to find the largest such color value among all possible valid paths. There's a catch though. If the graph has a cycle, like a loop you can get stuck in, then no path is considered valid in that way, and we should return -1. Let's look at an example to make this clearer. Suppose we have 5 nodes. Node 0 is node 1, is node 2 is node 3 is node 4 is, and the edges are from 0 to 1, 0 to 2, 2 to 3, and 3 to 4. One possible path is 0 to 2, then to 3, then to 4. The colors on this path are from node 0, then from node 2, then from node 3, and finally from node 4. If we count the colors on this path, appears 3 times and appears once. The most frequent color is, and it appears 3 times. So the color value for this specific path is 3. If this is the highest we can get, then 3 is our answer. Okay, so what's the first idea that might pop into our heads? We could try to find every possible path in the graph, calculate the color value for each one, and then pick the biggest. But if the graph has many nodes and edges, the number of paths could be enormous. That would be super slow. Also, we have to handle cycles. If there's a cycle, we must return -1. This hints that maybe something like topological sort could be useful, as it helps with ordering and cycle detection in directed graphs. So a brute force check of all paths is probably out. We need a smarter approach. Since it's a directed graph and we care about paths and cycles, topological sorting sounds like a good starting point. It processes nodes in an order, such that for every directed edge from node to node comes before in the ordering. If we can't process all nodes this way, it means there's a cycle. Now, for the color counts, we can use dynamic programming. Imagine we have a table, let's call it DP counts. For each node, and for each possible color, like through this table, we'll store the maximum number of times that specific color has appeared on any path that ends at that particular node. Here's the combined strategy. First, we'll build our graph representation, like an adjacency list, and also calculate the for every node. The in degree is just the count of how many edges are pointing into that node. We'll use a queue for our topological sort. We start by adding all nodes that have an in degree of 0 to this queue. These are the nodes that don't depend on any others. Our DP counts table, storing maximum color counts for paths ending at each node, will be initialized to all zeros. Now, when we take a node, let's call it from the queue to process it. First, we look at the color of node. We go to our DP counts table for node, and for its specific color, and we add 1 to it. This is because node itself contributes 1 to the count of its own color for any path ending at AC. After this update, the entry DP counts for node U and its own color tells us the maximum number of times colors U has appeared on a path ending at U. This value is a candidate for our final answer, so we'll keep track of the biggest one seen so far. Then, for every neighbor of let's call a neighbor, we need to pass on the knowledge from for every color. From 2 will update its entry in the DP counts table. It will take the maximum between what it already had for that color and what had for that color. This way, learns about the best color counts from paths that came through. Finally, we decrease the in degree of gress. If in degree drops to 0, it means all nodes that point to have been processed, so is ready to be processed itself. We add it to the queue. We also need to count how many nodes we successfully process from the queue. If, after the queue becomes empty, the number of processed nodes is less than the total number of nodes in the graph, it means some nodes were unreachable, because they were part of a cycle. In this case, as the problem states, we return -1. If we managed to process all nodes, it means there were no cycles, and the largest color value we kept track of during the process is our answer. This value represents the highest frequency of any single color on any path in the graph. Alright, here's what the Python code for this approach looks like. It might seem like a lot at first glance, but don't worry. We're going to walk through the key parts, piece by piece, so it all makes sense. We're essentially putting into code the ideas of topological sort and dynamic programming that we just talked about. First up, We initialize everything. We get the number of nodes. We create an adjacency list, called to store the graph structure. For each node, it lists its neighbors. We also create an adj list, initialized to zeros, which will store how many incoming edges each node has. We then loop through the given to populate our adjacency list, and correctly calculate all the in degrees. Next, we set up our dp counts table. It's a list of lists, where dp counts at index and subindex will store the max count of color for paths ending at node. It's initialized to all zeros. Finally, we prepare our queue for the topological sort. We go through all the nodes, and any node that has an in degree of 0 is added to the queue to kick things off. We also initialize a variable to keep track of the maximum color value we find, and another to count processed nodes. Now for the main loop, which runs as long as our queue isn't empty, we take a node from the front of the queue, let's call this U node, and increment our count of processed nodes. Then, we find the color of U node. We convert this color character, say, or into a numerical index, like 0 for 1 for and so on. We use this index to go into our dp counts table for U node and for its specific color, and we add 1 to that count. This reflects that U node itself is part of the path. After updating the count for U node's own color, that new count is a candidate for the largest color value. So we compare it with the quote max color value found so far, and update if this one is bigger. After dealing with U node itself, we look at all its neighbors. For each neighbor, let's call it V node. We iterate through all possible 26 color codes. For each color code, V node updates its entry in the dp counts table. It takes the maximum value between what it currently has for that color and what U node has for that same color. This ensures V node inherits the best counts from paths passing through U node. Then, we decrement the in degree of V node. If its in degree becomes 0, it means all its prerequisite nodes have been processed, so we add V node to the queue. Finally, after the loop finishes, we check if the nodes processed count is less than the total number of nodes. If it is, a cycle was present, and we return -1. Otherwise, we return the max color value found. So how efficient is this approach? For time complexity, building the graph in degrees takes time proportional to the number of nodes, let's call it n, plus the number of edges, m, that's order n plus m. The main loop processes each node and each edge once. Inside the edge processing, we loop up to 26 times for the colors. So it's roughly order n plus m times 26. Since 26 is a constant, we can say the time complexity is effectively big O of n plus m. For space complexity, we store the graph adjacency list, which can take up to order n plus m space. The array takes order n space. The dp counts table takes order n times 26 space, so the total space is also effectively big O of n plus m. This is pretty good for a graph problem. Alright, let's recap the main points. This problem involves a directed graph, paths, and color frequencies. The key to an efficient solution was to combine topological sort with dynamic programming. Topological sort helped us process nodes in a valid order, and, importantly, detect if there were any cycles in the graph. Dynamic programming, through our dp counts table, allowed us to keep track of the maximum count for each color on paths ending at any given node. And the crucial check, if the number of nodes we processed via topological sort is less than the total number of nodes, it means there's a cycle and we have to return -1. Otherwise, the maximum value we tracked in our dp table is the answer. Hope that explanation made sense and helped you understand how to tackle this problem. If it did, feel free to hit that like button, subscribe for more Leetcode breakdowns, or drop a comment if you have any questions or thoughts. And hey, if you're feeling extra generous, you know, the Boba Fund is always appreciated. Keep practicing, keep coding, and I'll see you in the next one. Bye for now.